Our topic today is rates of reaction. Actually, it's the greater topic of chemical kinetics, but that relates to how fast reactions run, or rates of reaction. The goal of these studies is to determine a step-by-step series of chemical reactions that combine together to make the overall balanced equation. That is the actual simple step-by-step at the molecular level series of reactions that happen to convert reactants into products. And we call that the reaction mechanism. And we're also trying to study how each step in that series of simple chemical reaction steps affects the rate of reaction. What this is all about is that an overall balanced equation such as the one at the top of this slide looks really simple, but what may actually happen at the molecular level may be quite different. And so this tells us about the starting, about what's consumed and what's produced, but we don't know the details of it. Down here at the bottom, I want to draw your attention to where you can see three steps in them, and those three steps together constitute the reaction mechanism for this reaction. There's the tert-butyl bromide just breaking up to become a tert-butyl carbocation. It's called such because there's a carbon that has a positive charge on it. And then it's also making bromide ion there. Well, that's the first step. The second step would be that carbocation we just mentioned reacting with a water molecule to make this kind of complex ion. This kind of complex ion might look like over here on the left, like this, with the water attached to the carbocation, and it has an overall positive charge. That same thing then gets used up by reacting with hydroxide ion, according to the way this third step is written, to make the alcohol that we were talking about in the overall balanced equation up here at the top, plus water. Now that water there was produced in the final step. That makes up for it being consumed earlier. And notice this carbocation with the water attached, this complex ion, was produced in the second step, consumed in the third. And so when you add these all up together, you will get the overall balanced equation, but this is supposed to be what's going on at the molecular level, and it's much more detailed than what appears to be going on from the overall balanced equation, where it seems that just a single hydroxide comes in and replaces a bromine to make it into a bromide. What else is on this page is two different versions of this three-step process, and it shows you that the steps are equilibrium reactions. We see here the kind of the 3D molecular representation, and here more of a 2D molecular representation. And this one down here has the H plus that's donated going to a water molecule, and this one has the H plus that's donated going to a hydroxide, which is why this makes a water molecule. And the water molecules are written funny here because they're trying to make it stand out that the unshared pairs of electrons on the oxygen are what are getting together with this carbon that's electron deficient in the carbocation. You can really see that nicely here. So, chemical reactions require collisions. This has to do with how fast reactions run. Chemical reactions involve breaking and forming of bonds. To break bonds requires collisions. To form bonds requires particles to get close enough to where they can start sharing electrons. So, chemical reactions require collisions. And for the reaction to happen, the collisions have to have enough energy. If they don't have enough energy, they'll just bounce off each other and not react. They also need to be favorably oriented toward each other as they collide, which means, in their 3D positioning relative to each other as they collide needs to allow the proper bonds to be impacted and broken, and the proper bonds to be formed. And if the molecules ran into each other from another direction, maybe, then you wouldn't have such a thing. You can just imagine that up here. If this water molecule ran into one of these outer CH3s, instead of the carbocation, even no matter how hard the collision, the reaction wouldn't happen. Okay, so let's talk about the energy of collision. This is a Maxwell-Boltzmann distribution plot. On the y-axis, we're showing how many particles have a particular kinetic energy. On the x-axis, we're showing what the kinetic energies are of the various particles. But if you picked a certain kinetic energy here and then just found how tall the graph was straight above that up to the plot, That height there would be the number of particles that had that amount of kinetic energy. If you summed up all those heights all the way through, you would have a count of every single particle in the whole sample. This is supposed to be representing, the way I've presented it here, two different temperatures for the exact same sample. The same number of particles in it, and therefore the same areas under the curve, but at two different temperatures. So the blue one's supposed to be the lower temperature, and I've marked it here near the peak because temperature is a measure of the average translational kinetic energy of the particles in the system, and so we only get one measure of kinetic energy, and it's the average when we take the temperature. But mind you, in any sample there's a whole spread of different kinetic energies, a whole spread of them, and the higher the temperature of the sample, the bigger the spread, the range of different amounts of kinetic energy. Okay, so this blue line here is supposed to represent activation energy, which we'll talk about more in detail later in this very video. But for now, I want you to think of it as the amount of energy, the minimum amount of energy required for the collision to result in a reaction. And so if two things collide, their combined energies need to equal this amount. Well, I'm oversimplifying here a bit, but what I'm going to say is that this is the cutoff for particles to be able to react. If they're above the cutoff, they have enough kinetic energy so that when they collide with a neighbor, there could be a reaction if the orientation is favorable. And so, if you wonder why reactions run faster when the samples are at higher temperatures, it's because of this. Look at graph T2. This red shaded area on the right represents the total number of particles that have enough energy to react when they collide with another particle. And that's a bigger fraction of the total area under the T2 plot than the blue shaded area here is for its total plot. So a smaller fraction of the total particles in the sample at temperature 1 have enough energy to react, and a bigger fraction of the particles in the sample at temperature 2 have enough energy to react. Chemical reactions frequently involve a series of simple reactions like we listed above when we were talking about a reaction mechanism. And these reactions produce and consume various quote-unquote intermediate species, and that's a technical term we'll be talking about. A reaction intermediate is a chemical species formed in one of the simple reactions in a reaction mechanism, then later used up during another simple reaction in the mechanism. So it wasn't there before, and it isn't there afterwards. That's why it's called an intermediate. Okay, so kinetics has to do with the details of the process to convert reactants into products. So far, like in thermodynamics, we've only been talking about reactants and products. So we talked about the before picture, like the reactants, and the after picture, the products, but not all the details in between. I want to point out that this is the reaction of octane, which you can take as a proxy for gasoline, and oxygen, when they combust to make carbon dioxide and water. I want to point out that this is a thermodynamically favored reaction. We see that the delta H would be negative, as indicated by this enthalpy graph. Is enthalpy on the y-axis here, and we've got the reaction progress or coordinate on the x-axis, as we've been used to, but we haven't been showing the hump in the middle. So the fact that there's less enthalpy in the products than the reactants means delta H is negative, and that means this is an exothermic reaction. And also, you can see that 34 gas products would be produced in the combustion, whereas only 27 particles were consumed. And so the fact that there is more disorder afterwards than there was before, as indicated by there being more gas particles afterwards than before, and by the way, octane would be a liquid, that indicates that this is entropically favored as well. In other words, there's been an increase in entropy, and both an increase in entropy and a decrease in enthalpy for a reaction mean that the overall reaction is thermodynamically favored. The delta G is negative. So this is a favored reaction, a thermodynamically favored reaction in nature, and yet you can have gasoline sitting out in the open air and it doesn't just spontaneously burn. It's not always burning, even though there's plenty of oxygen in the air. That's because there's a barrier that has to do with what has to happen between these things being present and these things being formed. So the reactants particles collide with each other and makes a bunch of different intermediates. A bunch of different intermediates whose enthalpies are indicated along the trace here in between reactants and products. There's a highest energy intermediate formed, and once that is formed, then the reaction is likely to proceed forward. That is called the activated complex or the transition state, and it's the least stable, the highest energy intermediate formed in the process. And so it turns out there's an energy barrier here. That's why these things have to collide with a certain amount of energy, is to be able to form an activated complex, which itself has a certain amount of potential energy that then can be released to make the products. And all this business in the blue box is what we're concerned with when we're dealing with kinetics. So I just mentioned the activated complex. It's the highest energy or least stable intermediate in a reaction pathway or a reaction mechanism. It's also called a transition state. Okay, there are 4 main factors affecting reaction rate. We've already talked about temperature, and you saw the Maxwell-Boltzmann distribution graph. And so what is the effect of temperature? It affects each particle's kinetic energy. So the higher the average particle kinetic energy, the more likely the reaction is to happen when the particles collide. And the more particles that have enough kinetic energy, the faster the reaction runs. Concentration increases how often or how likely a particle is to collide with its neighbors. The higher the concentration, the more that enhances the reaction rate. Particle size, which has to do with surface area, this is like if you have a solid inside an aqueous solution or something like that. Particle size will affect the rate. The smaller the particle size when you've got heterogeneous phases, meaning like a solid in a liquid or a liquid in a gas, the smaller the particle size, the faster the reaction, because reaction can only happen at the surface. But we're not going to deal with that much in this unit. And finally, catalysts can affect the rate. They affect it by helping to facilitate a favorable orientation or to create an alternate reaction pathway that's lower in energy. All right, so a catalyst, we just mentioned a catalyst. It's a chemical species that was present before reaction, it was involved in the reaction, and then it was reproduced in its original form to be present after the reaction is over. So it was there before and it's still there after. So it's the opposite sort of an intermediate. An intermediate wasn't there before and isn't there afterwards, but a catalyst is there before and is there afterwards. All right, here's an example of something that might be of interest to some of you. There's been a claim that the refrigerants known as chlorofluorocarbons, that they catalyze stratospheric ozone depletion, like the depletion of ozone in the ozone layer. And so down here in the middle, I'll just draw your attention to this right here in the middle. We see CCl2F2, so that's chlorofluorocarbon, and we see H nu, which is representing the energy of some ultraviolet light, and then that breaks off what's called a chloride radical because it's neutral in charge, but it's got an unpaired electron, and it's a very reactive species. So if it's present and there's ozone present, it can pull an oxygen off and make this kind of radical. Here's chlorine and oxygen radical, and then the ozone will have been turned into O2 gas in the ozone layer, or wherever this is happening. And then that chlorine with oxygen radical can get together with another oxygen radical, which in this other cycle you could see how those could be formed. And those together can remake the chlorine radical and also make some more oxygen. And so we had the chlorine radical before the reaction started, we have it after it started, so that makes that a catalyst, an example of a catalyst. Another place where catalysts affect us is that for all internal combustion gasoline-powered engines, they've had to have catalytic converters, which means in the flow of the exhaust before it goes out the end at the tailpipe, it has to pass through a catalyst, a catalytic converter that converts unreacted fuels into less toxic forms before they go out the tailpipe. And these are actually very expensive pieces. I've borrowed this, I guess it's an ad from Performance Technician. I hope they don't mind me using it for educational purposes. It's kind of a free plug for them, and I'm getting no kickback for it because they don't even know I did this. In any case, they're showing you that in here there's this kind of porous or mesh-like setup made of precious materials, often platinum or palladium. These surfaces of platinum or palladium tend to lodge previously unreacted pieces of fuel molecules with some oxygen, and then they produce carbon dioxide, water, and I guess they can also turn nitrogen oxides into nitrogen gas and oxygen. And so these things help with the environment, and they are actually, because they're catalyzing that reaction, there's still energy being given off, so these get really hot while the car is running, which is why you never want to drive a low car onto tall dry grass, because that catalytic converter under there is hotter than the regular exhaust, because combustion basically has been catalyzed right there, and unfortunately it's being catalyzed right there and energy is being released, but it's not doing anything to propel the car. It's just purifying the exhaust a little bit. Anyway, that's an application of a catalyst in your daily life. All right, so we've already talked about the activated complex being the highest energy intermediate, and maybe you remember something like this from your biology class. When a catalyst is involved, well, first of all, let's say that the barrier, the energy barrier that must be overcome in order for a reaction to run, that energy barrier we call the activation energy. That's this E sub A. And it's the difference between the energy of the enthalpy, let's say, of the reactants and the enthalpy of that activated complex or transition state. Well, when you put a catalyst in there, it lowers the activation energy, and it lowers the energy of the activated complex. So there's actually a new reaction pathway. Perhaps there are different intermediates. There's definitely a different intermediate where something has lodged against the platinum or palladium, for example, in the catalytic converter in a car and so forth. And so because this energy barrier is smaller, this reaction will go to completion faster. Now, if you're thinking back to the big K's, the capital K's we were talking about with equilibrium constants, all this means is it will reach equilibrium faster. It doesn't change the state of the equilibrium, it just changes how fast we get to it. Okay, so let's go back and connect that to the Maxwell-Boltzmann distribution, and here we've got the activation energy without a catalyst shown here, and then we've got the fraction of molecules or particles in the sample available to react, or with enough energy to be capable to react. And when we have a catalyst involved, well, the activation energy has been lowered, and so it turns out a much bigger fraction of the particles have sufficient energy upon collision to react. And so that's why things react a lot faster usually in the presence of a catalyst. Okay, so next we need to talk about how fast the reaction runs and compare it to an assembly line. I've done a little animation, it's a little crude, but what I want us to think about is that think of an assembly line, and these stations are like the steps in our reaction mechanism. And each step in the reaction mechanism runs at its own speed. So I'll show you the speeds here. The first, to go from station 1 to station 2, takes 72 seconds. To go from station 2 to, so basically station 1 takes 72 seconds to run. Station 2 takes 2 minutes to run. Station 3 takes only 48 seconds to run, and that will produce station 4, which I guess station 4 we could have called the product. Okay, so it turns out that you can see, obviously, if it's taking 2 minutes for station 2 to run, then we should be piling up the products from station 1 at station 2. And if it takes 2 minutes for station 2 to run, then station 3, which can complete its process in 48 seconds, it's sitting there idle most of the time, right? Because every time something is given to it from station 2, then the station 3 rapidly processes it and sends it on to station 4, so, or to products. And so if these are the only 3 rates we have to worry about in here, the 3 reactions, 1, 2, and 3, and if station 4 is our product, if these are only 3 reactions we have to worry about, and they're running at these various rates that are shown, then clearly station 2 is the bottleneck. It's the one we could never, run one reaction all the way from start to finish in under 2 minutes, because it takes at least 2 minutes for station 2 to get done. So if station 2 gets done, if that was step 2 in our reaction pathway, then that would limit how fast we could run the reaction. It would be the rate limiting station. It would be the rate limiting step in our reaction mechanism, and that would dictate how fast our reaction could run. Well, let's look at a reaction mechanism here, again, for a very simple process. NO2 plus carbon monoxide gas makes nitrogen monoxide and carbon dioxide gas. And that's the overall balanced equation, but it doesn't happen that way at the molecular level. You might think just a carbon monoxide smashes into a nitrogen dioxide and pulls an oxygen off, but no, it's not that simple. So here's what they believe happens at the molecular level. One nitrogen dioxide crashes into another nitrogen dioxide and makes a nitrogen monoxide and a nitrogen trioxide. And then that nitrogen trioxide reacts with a carbon monoxide to make nitrogen dioxide and carbon dioxide. They say the second step is really fast. They say this first step is slow. And just like we talked about on the previous slide, the slowest step dictates how fast the reaction can run. The final products can't be made any faster than the slowest step can run. Okay, so notice that nitrogen trioxide was not a reactant, not a product. It was formed by one of the steps and consumed by another one of the steps, and so it's not present before and it's not present after, and so we would call that an intermediate, right? And so after cancellation, we're going to end up with the overall balanced equation. Well, it turns out that what we're trying to do here is create a rate law for the reaction. The rate law for the reaction is an equation that shows the dependence of reaction rate upon concentrations of reactants and or products that affect it. So it's an equation. It's a math equation with an equal sign. And it shows how the speed of reaction depends upon the concentrations of the various reactants or products that affect that speed. Okay, so it corresponds, for our purposes, to the reactant side of the slow step in the reaction mechanism. The reactant side of the slow step. Let's look back here. The reactant side of the slow step was NO2 plus NO2, right? Okay, so the slow step is sometimes called the rate determining step. That's sometimes abbreviated as RDS, or the rate limiting step, sometimes abbreviated as RLS. All right, so in this example, the rate law for the reaction of nitrogen dioxide plus carbon monoxide is nitrogen monoxide plus CO2. The rate for that rate law for that reaction, which is based upon the proposed mechanism, is rate equals a lowercase k. That's a kinetic rate constant. It's some constant that's only good for a particular temperature for that reaction, times the concentration of NO2 squared. Why should that be squared? Well, it's squared because in the slow step, we had a coefficient of 2 for the NO2, right? NO2 plus NO2. That would be 2 NO2. That's why there should be a square on this NO2 concentration. Why does the carbon monoxide concentration not get to be in this rate law? It's because it's not involved in the slowest step of the reaction. It is not involved in this slow step, and the slow step is what dictates how fast the reaction runs. It's involved in a fast step. So it's not that it can run, the reaction cannot run without carbon monoxide. It has to have carbon monoxide present. But you can increase or decrease that amount and it won't affect how fast the reaction runs. But if you increase or decrease the concentration of NO2, well, that's going to affect how fast the reaction runs. And so this rate law right here, this math expression, explains to us how the speed of the reaction depends on the concentration of the reactants.